അപ്പോൾ ഇതൊരു എക്സാമ്പിളാണ് ലെങ്ത്. ഇപ്പം നമ്മൾ ഇതുവരെ ചെയ്ത് വെച്ച് നമുക്ക് ചെയ്യാവുന്നൊരു പ്രോബ്ലമാണ്. ഓക്കെ, ഒന്ന് ചെയ്ത് നോക്കാം ജസ്റ്റ്. അപ്പോൾ ഇതാണ് ക്വസ്റ്റ്യൻ. 2 trains A and B, okay, have proper length, each have proper length L, and രണ്ടിന്റെയും proper length L ആണ്. Each have proper length L and move in the same direction. A speed is 4c/5 and B speed is 3c/5. Okay. A starts behind B. How long as viewed by a person C on the ground? Okay. So there's some other person C on the ground. Okay. Now, how long as viewed by a person C on the ground does it take for A to overtake B? Okay. By this we mean the time between the front of A passing the back of B and the back of A passing the front of B. Right? Is this clear? So what's happening here is there are 2 trains, each have proper length L, which means in the rest frame the length is L. Now some other observer C is watching these trains, okay, and how much time does it take for it to overtake? Okay, how much time does it take to overtake? So in order to overtake, what happens? How much distance has it to travel? Right. So the front. So if they come like this, it will have to travel a length L. Right. So the train has to move by a length of twice its length. Right, by a distance of twice its length in order to overtake it. Right. So if it moves once its length, it will come here. If it moves L, it will come here. Okay, one more L, it will completely overtake. All right, so it's twice the length. Okay, twice the length of the train. Is that clear? The distance that it needs to travel is twice the length of the train. Okay, that's the thing that we need to realize here. Right. Is that clear? All right.
Yes, sir.
So let's try to do it. Now, twice the length of the train, that's fine, but we also have length contraction. Okay. So we need to find the length of these trains as observed by C. Okay. First, we need to find the length of these trains as observed by C. Okay. So for C, these trains are moving. So let's just say LA, length of the train as observed by C. Okay. That's what I write by LA. Is this fine? So it's the length of A as observed by C. C is the observer at ground. And with respect to C, this train is moving at 4c/5. Right? So we know this result. This is equal to L square root of 1 minus velocity of A C square. Right? This is the length contraction formula that we had. So this is equal to L multiplied by square root of 1 minus what's VA square? That's 16/25. Right? There's a C square there. There's a C square in the denominator here. Okay, so they get cancelled. So this is equal to 25 minus 16 is 9. So this is simply 3L/5. Am I right? LA is equal to 3L divided by 5. Okay.
Yes.
Now we can also calculate LB. LB is equal to, okay, this is L multiplied, both have proper length L, okay, square root of 1 minus, so this is V square by C square, V is 3c/5, so it is 9c square by 25 by C square, so it's 9/25. Okay, so 25 minus 9 is 16, so it's 4/5. Am I right?
Yes.
So according to C, these 2 trains have different lengths. These 2 trains have different lengths. Now we need to, so according to C, he is seeing these things as different lengths, LA and LB. Right? So in order that this back of A crosses the front of B, okay, only then we can say it has overtaken. The total length traveled would be LA plus LB. Right? If they are the same length, it's twice the length. But in this case, it is LA plus LB. Is that correct? The total length the train has to travel is LA plus LB. Right? Is that clear? Yeah, only when the train travels a distance of LA plus LB, we can say that it has overtaken the other train, right? So we assume that they are starting. We are looking just as it coincides. The front of A coincides with the back of B. Okay. Okay. So by traveling a length LA, the train will reach here. Then it has to travel a length LB in order to completely overtake it. Okay. So the total distance to be traveled, when you say that it overtakes, the total distance to be traveled is, let's say the distance, I'll write it as D. Okay. LA plus LB, that's equal to, so it's 7L by 5. You just add these two lengths. Right? Add these two lengths. 4L by 5 plus 3L by 5. Okay, is this fine? This is the distance that the trains have to, the train has to travel in order to overtake it completely. This is also fine. Okay. Right?
Yes, sir.
Right. Now, what do we need? We need to find the time between the front. We need to find the time taken for this train to cross this distance. All right. What's the time taken by this train to cross this distance? So we need the velocity. Right? Velocity means the relative velocity. Right. So how fast does A move away from B? Right. We need the relative velocity. How fast does A move away from B? What's the relative velocity of A with respect to B as observed by C? Is that correct? Because we are talking about C's point of view. So we also need one more information. What's the relative velocity of A, or what's the velocity of A with respect to B as observed by C? So we need also to find velocity of A, okay, with respect to B as observed by C. This means the relative velocity. Okay, how fast do they move away with respect to C? Now, how do we calculate this? What's the relative velocity?
On my
Yes.
VS
Can you think how to find the relative velocity as observed by C? Okay, we have discussed this actually. All right, so if you need to find the velocity of A with respect to B, you will have to do the velocity addition formula, right, using the relativistic velocity addition. If you need to find the velocity of B with respect to A, you also need to use velocity addition or subtraction. Okay, we call it the velocity addition rule, right? But we are talking about another person, C, right? So with respect to C, how fast are they moving apart? How fast are they separating? That's the question, right? We have discussed this, right? Because when C looks, he sees that it's one train is moving at 4c by 5, another train is moving at 3c by 5. So the relative velocity is simply, let's call it as V relative, okay, as seen by C. This is simply 4c by 5 minus 3c by 5. Is that correct?
Yes.
Yeah, because as we have said earlier, we don't have to use the velocity addition formula when you are talking about the relative speed as observed by another observer. Right? When do you use the velocity addition formula? When you need to find the velocity of A with respect to B or B with respect to A, you need to find the velocity addition formula. But this person is seeing A moving at 4c by 5 and B moving at 3c by 5. This person just sees this, all right? So how fast do they move apart? It's just 4c by 5 minus 3c by 5. Is that clear? We said that in this case, the speed can exceed the speed of light. The relative velocity as observed by C can exceed the speed of light. We have discussed this, all right? Okay. So this is actually C by 5. Okay. So we've got the relative velocity. We need to see, we know the distance, okay, that C says the train has to move. So we have all the details, all right? So we have this velocity is equal to distance by time. So time is equal to velocity by distance. So that's equal to, so the time taken, let's simply write as delta T as observed by C. Okay. So delta Tc equal to the relative velocity divided by distance. Okay. All right. Wait. Sorry, it's distance by velocity. I'm sorry. Right. So time taken is distance by velocity. Right. So the distance is 7L by 5. Okay, 7L by 5 divided by velocity. So it's 5 by C. Right. So that's equal to 7L by C. That's the distance, that's the time, okay, that A takes to overtake B as observed by C. And this is also a trick question because people often make this mistake, right? When you calculate the relative velocity, if you use the relative velocity addition formula here, you are wrong. Okay, then you are getting some other velocity. Because remember that when some other observer is, so according to this observer, both A and B have some speed 4c by c and 3c by 5. All right. So he will just see that they are moving away at the difference of their speeds. All right. He'll see that it's slowly overtaking. Now, what happens if they were moving in the opposite direction? This is 4c by 5 like this, and 3c by 5 in this direction. Okay. Yeah, then C would say that they are moving apart at a speed, all right? They are the relative velocity, the separation speed is the addition of this. So that would be 7c by 5. And you see that this is greater than C, right? If they are moving away, the relative velocity as observed by C would be 7c by 5. And this is greater than C, and this is allowed, all right? It's not the velocity of any object, it's just the relative velocity as observed by some other observer. I hope this is clear. Is this fine? Any questions?
Yes, fine. Sir, നമ്മളെ velocity is VA plus V by divided by addition ആണെങ്കിൽ 1 plus VA into VB by C square എന്ന് പറയുന്ന ഫോർമുല നമുക്കുണ്ട്.
അതെ.
ഇവിടെ കൊടുക്കേണ്ട ആവശ്യമില്ല അത്.
ഇല്ല. റിലേറ്റിവിറ്റിയുടെ വെലോസിറ്റി അഡീഷൻ ഫോർമുലയാണ് ഉദ്ദേശിച്ചത്.
അതെ.
അതാ പറഞ്ഞത്. You have to be very careful. What do you need to calculate? Okay. So if this is the situation, and if the question is this, what is speed of A with respect to B? Right? What's the speed of A with respect to B? Then you will have to use the velocity addition formula. Right? That would be 4c by 5 minus 3c by 5 divided by 1 minus, you see, so 12c square by, so the VA VB by c square, right? So that, right? So you will have to use this VA VB by c square. You have to use this. All right. Okay. Now, if the question is
A and B ആയിരുന്നെങ്കിൽ നമ്മൾ നേരത്തെ ചെയ്യുന്ന പോലെ തന്നെ divided by 1 plus.
Exactly. And നമ്മൾക്ക് അടുത്ത പ്രോബ്ലത്തിൽ അതാണ് നമ്മൾ ചെയ്യുന്നത്. ഈ കൺഫ്യൂഷൻ ഒഴിവാക്കാൻ വേണ്ടിയിട്ടാണ്. It's a very subtle issue. Okay. ആദ്യം പഠിക്കുമ്പോൾ ഇത് കുറച്ച് കൗണ്ടർ ഇൻറ്റ്യൂറ്റീവ് ആയിട്ട് വരും. So you can ask also the question, what's the velocity? What is speed of B with respect to A? This can also be asked. Okay. Then you would have to do VB minus VA divided by 1 minus VA VB by c square. In these two situations, you have to use the relativistic velocity addition formula. Okay.
Okay, sir.
But here, what's the question here? What's the relative velocity as observed by another observer who is at ground? Right? So the C sees A moving at 4c by 5. The same person sees B moving at 3c by 5. All right. So what's the relative velocity from the same frame? That's the question. Okay. So he just has to add or subtract the velocities depending on their directions. Is this clear?
Clear.
I'll just explain this, all right, for the sake for the.
Clear, sir. Thank you.
All right. I'll just for the record, I'll just explain it. Okay. So suppose we have two objects, A, B, right, and their velocities are VA and VB with respect to the ground. Okay, and we have got the ground here. Now there are three questions that you can ask. Okay, you have to be very careful. There are three questions that you can ask. What's the velocity of velocity of A with respect to B, that he can ask. Okay. Second, he can ask velocity of
A with
B
respect to G.
with respect to A. Okay. You can also ask a third question. What's the relative velocity
With respect to
of
G.
A and B with respect to ground? Okay. These three questions you can ask. In this question, its velocity of A with respect to B. It would be VA minus VB divided by 1 minus VA VB by C square. Okay. The velocity of B with respect to A, that would be VB minus VA divided by 1 minus VA VB by C square. Okay. This is the place where we have to use the relativistic addition of velocity addition formula. Okay. Here, this situation is different. What's the relative velocity of A and B with respect to the ground? Right. That would be simply VA minus VB. Okay. Now, if they are traveling at opposite, if they are traveling in opposite directions, okay, if they are traveling in opposite directions, this is VA and this is VB. Okay, so velocity of A with respect to B would be, this is with respect to ground. Okay. Velocity of A with respect to B would be VA plus VB divided by 1 plus VA VB by C square, and velocity of B with respect to A would be again VB plus VA divided by 1 plus VA VB by C square. Right? You can also ask a third question. What's velocity, relative velocity with respect to ground? All right, that would be simply VA plus VB. Okay, and suppose, okay, for example, suppose VA is equal to, let's say, C by 2. Okay, and VB is equal to let's say 3C by 4. Okay, both these are less than C, right? What would be the relative velocity with respect to ground? VA plus VB would be C by 2 plus 3C by 4. And you see that in this case it's equal to 2C, 5C by 4. Am I right? Is that correct? Yeah. That's 5C by 4. And you see that this can be greater than C, no problem here. There is no contradiction. Okay. So the relative velocity as observed by someone else, okay, can be greater than C. Relativity does not say anything about this, right? So usually we say that the speed observed can never exceed the speed of light, but in this case you see that it's not a velocity of any object, it's just a relative velocity for some observer. This can exceed the speed of light. Okay. So this you have to be very careful, because usually when we see in relativity something is greater than C, we have an instinct to say that it's wrong, because we know that nothing can travel faster than the speed of light. All right. Here it's true, nothing can still travel faster than the speed of light. Nothing is traveling at the speed faster than light. All right. The only thing is the relative velocity. This is not the velocity of any object in any frame. It's just the relative velocity as observed by some observer. Okay. All right. I hope that's clear. Now, again, here is another question. So we will answer both these questions and then this should be clear. Right? How long, as viewed by A and as viewed by B, does it take for A to overtake B? All right. So, and vice versa. You can also ask the opposite question. All right. So this is the first part of the question. What we did was, we had a third observer C, and we asked the question, what's the time taken as observed by C? All right. Now here is the question, how long as viewed by A? Okay. So first let's take A's point of view. Okay. So how long as observed by A, all right, does it take for A to overtake B? Okay. Right. So here we have to find the relative velocity. Okay. So we need to find what's the velocity of B as observed by A. So that you can write velocity of B as observed by A. All right. We have to find the velocity of B as observed by A. Okay, so velocity of B as observed from the ground is 3c by 5. All right, and the velocity of the frame itself, of the A itself, is 4c by 5. Is there any question as to whether it's a minus or a plus here?
Minus.
All right.
Divided by 1 minus v.
Yes, so that would be, how much is it? 12 c square by 25. Is that correct? So it's 12 by 25. Is it? Okay, let's just write it. VA VB by c square. Okay, so that would be 12 c square by 25 c square. VA VB by c square. Is this correct? I think it's correct. So this is equal to minus c by 5 divided by 25 minus 12. That's 13, right? So that's equal to minus c by 5 multiplied by 25 by 13. So that's equal to minus 5c by 13. Is this fine? I think it's correct. Did we do it correctly?
Yes.
Okay. So it's 5c by 13. What does this minus mean? This minus means that, okay, you see here, with respect to the ground, okay, we'll just get the physics right here. Okay. So with respect to the ground, what's happening with respect to the ground? You see that A is traveling faster than B, right? With respect to the ground, A is traveling faster than B. Okay. So from the viewpoint of A, what would he see? He would see that B is traveling in the opposite direction, right? Because we see that A is actually traveling faster than B. So when in the viewpoint of A, he will see that B is just traveling in the opposite direction with the speed 5c by 13. Is that correct? Okay. It's just like you're looking at if you are driving, right, and you are overtaking this. If you are overtaking this bus, which is moving at some velocity v1, and you are moving it with some velocity v. So from your car, you would see that the bus is actually moving backwards, right? From your car or from your bike, you would see that this bus is actually moving backwards with respect to you, right? If you are looking only at the bus. And at a velocity which is equal to the difference of this velocity, right? And we'll have the relativistic correction factor. Okay, that's fine. All right. Now for A, so A can imagine that he is at rest. Okay, there's no problem. A can imagine he is at rest. Okay, and he says that, all right, there's a train B which is passing, which is moving in the opposite direction with the speed 5c by 13. Okay, and what would be the length of B as observed by A? Let's write as L prime B. Okay, so what is this? This is, so we need to find length of B as measured, okay, as measured by A. Okay, so he sees that A sees that B is moving at the speed 5c by 13. So that would be the proper length multiplied by square root of 1 minus v square by c square. In this case, it is equal to 25 by 169. Is that correct? V square by c square, right? Okay, because L, the proper length is given as L. So we can write this as LB prime, okay, just with respect to A. And this is equal to 169 minus 25 is 144. That's 12 by 13 L. Am I right?
Yes.
Yeah. So A is this length. All right. And what's the length of A as observed by A? That would be L itself, right? Because A is at rest. So LA as observed by A, let's write it as prime. LA prime is equal to L itself. We are talking about the length of A with respect to A. Okay. So total distance that the train has to traverse would be, let's write it as D prime is equal to L plus 12 by 13 L. Is that correct? This is the total distance for overtaking as observed by A. Is this clear?
Yes, sir.
Okay. So this is equal to 13 L plus 12. That's 25 L, right, divided by 13. Is this correct? Yeah. Yeah, so this is the distance. All right, so we have got the distance traveled, we have got the velocity, we've got the speed, so we just need to find the time taken. Okay, so we know that velocity is distance by time and time is distance by velocity, right? So distance we have got here, it's 25 by 13L, okay, divided by velocity. The velocity is 5c by 13, so it's 13 by 5c. Okay, so that's equal to, what is it, 5L by C, right? 5L by C. This is the time for overtaking as observed by A. Fine. All right. Now the second question: how long, as viewed by B, does it take for A to overtake B? So we have seen now three perspectives. First, we looked at the perspective of C. We looked at the perspective of A. Now we need to look at the perspective of B. All right. Now the perspective of B would be, B will say that the relative velocity of, so A is saying that B is moving at a speed 5c by 13 in this direction. So B would, you don't have to do the calculation. B obviously will say that A is moving in the opposite direction with the same speed. Okay, so velocity of A, we can check it, velocity of A with respect to B, because this velocity is relative. It would be simply 5c by 13, and you'll get exactly the same answer. All right, because A is saying that B is traveling at a speed 5c by 13 in the minus x direction. So according to B, the relative velocity would be 5c by 13 in the forward direction. That the result you will get would be exactly the same, because the train's proper length are the same. Both have proper length L. So in the end, you will get exactly the same result, right? So you will see that, all right, so that's 5L by C. And let's see what the answer we got. So here it is 7L by C. See, it is 7L by C. From the perspective of C, C says that the time taken is 7L by C, and A and B say that the time taken for overtaking is 5L by C. Okay, all right. So that's how you do it. We have done all the three cases here. That's it. It's a good question because it clears some of the concepts. So you really have to think, okay, what's the velocity that you need to measure, okay? All right. Let's do another problem with Lorentz transformation. Okay, again, you have to be careful here. I didn't write it down, so let's. Okay, is this fine? Is there any doubt in the previous question? Okay, that clears so many concepts. Okay, we have done three cases, and you need to be familiar with all three without any confusion. Is there any doubt there? We can ask now. Okay, fine.
Yes.
Okay. Now, here is another question. A train with proper length L. Okay, I'll just write it here. A train with proper length is given as L. Okay. A train with proper length L moves with speed 5c by 13. Moves with speed 5c by 13. Okay, with respect to the ground. A ball is thrown from the back of the train to the front. Okay, there's a ball thrown from the back of the train to the front. Okay, the speed of ball with respect to the train is c by 3. Okay, let's write it as u. U is equal to c by 3. What is this? Okay, we can write u with respect to train. I'll write it as ut. Velocity of ball with respect to train is c by 3. Is this clear? So from the train, the ball is thrown at a speed c by 3. Okay, this is with respect to a train. As viewed by someone on the ground, how much time does the ball spend in the air? Okay, as viewed by someone on the ground. Okay, how much time does the ball in the air? Okay, that's the question. All right. And how far does it travel? And how far does it travel? Okay. So here we are given the perspective with respect to a frame called the train frame. Okay, we have got the perspective of the train frame. All right. We need the perspective of the ground frame. Right. The train frame will write with us the suffix. What do you say? Yeah. Is this called a suffix? Subscript. Okay. The train frame will write with the subscript T, and the ground frame will write with the subscript G. Okay. So we won't use any prime or anything here. We'll just do it physically. Now, can you do this? How can you do this? Of course, there's a right way and a wrong way of doing it. Okay. You could use the length contraction formula, right, and use the velocity and find the time, and you would be wrong. You would be wrong. All right. So you shouldn't do that. You have to use the direct Lorentz transformation. All right, because it doesn't matter what the length of the train is with respect to the ground. That doesn't matter. We are asked this question: how far does the ball travel? How much distance does the ball travel with respect to the ground? They don't ask they don't ask the length of the train as observed from the ground. They are asking how far does it travel with respect to the ground. Okay, right. So let's just write down what we have. All right, what we have is, we have got the length of the train. Okay, or we can okay, let's write the distance. Okay, the distance moved. Let's write the train frame first, then we'll use the Lorentz transformation. In the train frame, things are simple. Okay, what's the distance traveled? Let's say delta x with respect to a train. Okay, delta x with respect to train is L. Okay, because the question is given, the ball is thrown from the back to the front. The ball is thrown from the back to the front. So the distance traveled, okay, delta xt. In the train frame, the distance is, or the separation is L. That's given. Okay, all right. And we are given the velocity of ball with respect to a train is c by 3. Okay, so what's the time taken with respect to the train? What's the time taken with respect to the train, right? So we know that velocity is distance by time. So time is distance by velocity, right? So distance is L divided by c by 3. That's equal to 3L by c. Is this clear? Is this fine?
Yes, sir.
Now we need to go to the ground frame. Okay, we need to go to the ground frame. So now we can ask the question, delta xg and delta x, sorry, delta tg. These are the things we are asked to find. Delta t with respect to the ground. Okay. So we can either use, so you can see that with respect to a train, the ground is moving at 5c by 13 in this direction. All right. So with respect to a train, the ground is moving at 5c by 13 in the opposite direction. All right. So you would you can use the Lorentz transformation formula. So this would be gamma, okay, delta x train. What was the formula? What was the formula for that?
Vx by c.
Vx by c square. All right. Is it plus or minus? Plus or minus?
It's plus.
Okay, plus. Very good. Okay, because you see that this with respect to train, this ground is moving in the opposite direction with respect to 5c by 30. If they are moving in the same direction, you would have a minus. Am I right? Okay, what about delta tg? That's gamma. Delta t plus, what is it? What do we have here? The Lorentz transformation formula. What is it?
V delta.
Oh, I'm sorry. Here it's not this, right? What is this here? What's the transformation for coordinate? It's delta x plus.
It's
just
1 minus.
Yeah, v. Am I right? X plus v delta t, right? Yes. You just look at the Lorentz transformation formula, right? We had this formula here. Yes. Okay, so we have got this x prime is equal to gamma x plus. We call this as the inverse Lorentz transformation. So we can write Lorentz transformation like x minus vt. Is this correct? And t prime is equal to gamma t minus v by c square x. Right? Is that correct? So in this case, we have got velocity with the minus sign. So we'll have a plus there. That's what we are using here. Okay, gamma delta xt plus v delta t. Okay, that's that thing. And here it would be v by c square delta x with respect to the triangle. Okay, so I think she's talking to someone else. Right. Is this clear? The formula that we have used, is this clear? These are just what we called as the inverse Lorentz transformation, but it doesn't matter. Inverse Lorentz transformation is also a Lorentz transformation. We are just use the Lorentz transformation formula. Is this clear?
Yes.
That's all right. Good. Now we need to find, we can find gamma. Gamma is equal to 1 by square root of 1 minus v square by c square. What was the velocity? V square by c square. V square by c square, right? What's the velocity? It's 5c by 13, right? So it would be 25 by 169, and that would be 1 by square root of 144 by 169. Okay, that would be 12 by 13. So it's equal to 13 by 12. The gamma factor is 13 divided by 12. You know, you just substitute in this formula and you get the result. Okay. Okay. And delta xg. Okay, so what's the distance traveled with respect to the ground? That's equal to 13 by 12 multiplied by delta xt is L itself, okay, plus V is given, V is 5c by 13, okay, just substitute all these things. We got 5c by 13 and delta t, that's also given here, it's 3L by c. Okay, so we have used this velocity of the ball here, all right. That's the easiest way to do it. Okay, so you see that this is equal to, what is it? 13L, so it's 28, 13 plus 15, 28, am I right? Okay, so it's equal to 13 by 12 multiplied by, what do we have here? You just add these things, so it's 13L plus 15L, so it's 28L divided by 13, right? Yeah. So these get cancelled and you can divide 4 by 4 and that would give you 4L by, sorry, just 28 by 12, that's equal to 7L by 3. That's the This is the distance traveled by the ball with respect to the ground. All right. So you be very careful here. In this case, the distance traveled from the train frame is L. That's given. All right. The distance traveled by ball is in the train frame is the length of the train. That's given. Okay. This is given. Right. And this is not the length of train as seen on ground. Okay, so you shouldn't make this mistake. It's easy to make this mistake because the velocity is given. You may calculate the length of the train with respect to ground using the length contraction formula and then divide it with the velocity, but the time you get is different. That's not the thing that we are looking for. All right, so you have to remember that in the train frame, the ball travels. In the train frame, the ball travels. Okay, so I'll just make it clear. In the train frame, ball travels distance L, which is the length of the train. Okay, length of the train. All right, and we can calculate the length of the train from the ground, but that would not be the distance. So the distance traveled as seen from the ground is different. It's delta xg. Okay, there's this extra factor there. All right, we can also find delta t from this thing. Is this clear? So in this case, what we have done is we have made a simple calculation. What we did is that we first wrote down the coordinates in the train frame. That's what we did. Okay. We first wrote down the coordinates in the train frame, which is easy, and we had to use the velocity here to write down the time. So we have written this down, and then we use just the Lorentz transformation formula. Okay. Is this clear? Okay. So okay. We can also find delta t with respect to the ground. Okay, so we have got the formula here. Just substitute all these things. Gamma we already found out. That was 13 by 12. Okay. Delta t on train that we have got here. We have got it here. It's 3L by C. 3L by C multiplied by V by C square. Okay, can you just so it's just add plus V by C square. So it's V by C square. What was V? V was 5C by 13. Okay, so it's equal to 5 by 13C and delta xt. That's given us L. Okay, so you just do this, and the answer you get will be 11L by 3C. Just do this. Okay, so these are the answer. These are the answers. So this is the time that the ball would spend in the air as seen by the ground. It's 11L by 3C, but according to the train, that is 3L by C. That's 3L by C. So you see that these times are different. Okay, is this clear? Any question? It's fine. Okay, shall we go to the next one? If you have any question, doubt, you please ask. Okay, this may seem confusing, but if you do it really systematically, it's not difficult. Can you solve these kinds of problems? Is it easy? Is anyone there?
Yes, sir.
Okay, it's clear, isn't it?
Clear, sir.
Okay, so if you have any doubt, you can ask. Okay? Now let's do another problem.
സാറ് പറഞ്ഞു തരുമ്പോ എടുക്കാൻ പറ്റും, പക്ഷെ നമുക്ക് തന്നെ ഇങ്ങനെ അങ്ങോട്ട് സോൾവ് ചെയ്യാൻ പറ്റുന്നില്ല സാറേ.
ഓക്കെ, അത് കുറെ സിറ്റുവേഷൻസ് നമ്മൾ പ്രോബ്ലം ചെയ്ത് പ്രാക്ടീസ് ആകുമ്പോൾ ചെയ്യാൻ പറ്റണ്ടാണ്. നമ്മൾ യു ഹാവ് ടു ഗെറ്റ് യൂസ് ടു ദീസ് സിറ്റുവേഷൻസ്, സോ ദാറ്റ് യു ഷുഡ് ബി ഏബിൾ ടു ഇമാജിൻ. സോ യു ഹാവ് ടു ഡു മോർ പ്രോബ്ലംസ് ആൻഡ് പ്രാക്ടീസ്.
Okay,
So
sir.
you, when I give the notes, when you study, you try to solve this without looking at the solution.
Okay, sir.
So only then you learn. You shouldn't look at the solution always. You just try to solve these problems without looking at the solutions. Then you know what information is missing in your head. So that's the only way you can do it.
Okay, sir.
These situations are a bit confusing, I agree. But the situations are a bit confusing, but such problems are asked always because confusing situations, it makes a good question, right? Okay. And when you practice, if you have any question, you can ask me. We'll clear these doubts, all right? If you have any confusion, whether it's to add or subtract, which formula to use, how to know which formula to use. If you have any doubt, you can just ask and then we'll clarify. Okay.
Okay, sir.
Okay, let's do another problem. Proper lifetime of a particle is 5 nanoseconds. Okay. Proper lifetime of a particle is 5 nanoseconds. Okay. So let's write. Proper lifetime of a particle is 5 nanoseconds. So it's 5 multiplied by 10 raised to minus 9 seconds. Is that correct? 5 nanoseconds?
Yes.
10 raised to minus 9 seconds. Okay. So that's given. Calculate the distance traveled by the particle before its decay in lab frame, where its lifetime is 10 nanoseconds. So let's write this as delta tau. Okay, delta tau. In the lab frame, its lifetime is 10 nanoseconds. So I'll write this as delta t in the lab frame. This is given as 10 nanoseconds. 10 into 10 raised to minus 9.
Calculate എങ്ങനെയായിരുന്നു സാറേ? With respect to lab.
Question is calculate the distance traveled by the particle. Distance traveled by the particle. Distance traveled by the particle before its decay. Excuse me, just a second. So, can you hear me?
Yes.
Okay. So, calculate the distance traveled by the particle before decay in the lab frame. Okay. Now, you look at this question, right? Maybe we can write this as delta t and delta t prime. Okay, we can write as delta t and delta t prime. All right. Now, just look at this question. Do we have enough information to solve this problem? Do we have enough information to solve this problem? You just think of a way we can
T
solve.
prime ഏതായിരുന്നു സാറേ എഴുതിയ?
എന്താണ്?
With respect to delta t prime.
Delta t prime എന്ന് പറയുന്നത് lab frame.
Okay.
What's the delta t prime? As I have, delta t prime here is the lifetime in the laboratory frame. Okay, the lifetime in the laboratory frame. Time in laboratory frame.
10 nanosecond.
Yeah, this is the lifetime in laboratory frame. This is the proper lifetime. Okay, so the question is this: calculate the distance traveled by the particle before decay in the laboratory frame. Okay.
ആദ്യം ടൈം വ്യത്യാസം. ആദ്യം ടൈമിലെ റെസ്പെക്ട് വേരിയേഷൻ കണ്ടുപിടിക്കും.
വേരിയേഷൻ മനസ്സിലായില്ല. Is the question
distance clear? Yes.
All right.
Proper lifetime തന്നിരിക്കുന്നു. Lab frame തന്നു.
Yeah. You need the distance traveled. You need the distance traveled. You see that there is no velocity given here. Okay. You see that there is no velocity given here. All right.
Yes.
So when this question is asked, you may think that the information is incomplete. Okay. Is the information incomplete to solve the problem? Okay, you may be tempted to say that there is incomplete information, okay, because the velocity is not given. All right. If the velocity is given, you could find the gamma and use the Lorentz transformation equations, right? And maybe you can do something there. All right. But actually, that's not true. There is an information that we can use. All right. The information is that there's a quantity, this quantity called, we can say that there's an invariant quantity. We can use a relativistic invariant quantity or a Lorentz invariant, which we discussed in the last class. We said that this quantity, right, c square dt square minus dx square, right? This is a Lorentz invariant quantity. In whichever frame you measure this quantity, all right? We didn't come to the real physical. We said that this is the proper time, etc. Right? This is associated with proper time, but you don't need. You can just use this information, all right? This quantity is invariant, all right? In whichever frame you measure, this quantity is invariant. I've written just one spatial dimension, all right? If you have 3 spatial dimensions, you would have minus dy square minus dz square minus dy square, right? Is this fine? Okay.
Yes.
This is the Lorentz invariant quantity. We can use this information to find the distance. Okay. Now let's look at this frame. Okay. Let's look at the particle frame. Let's look at the particle frame. In the particle frame, it decays after a time. Let's say dt is 5 into 10 raised to minus 9 seconds. Okay. So in this frame, it doesn't move any distance. This is the proper lifetime. So it doesn't move any distance. Okay. So you can take dx equal to 0. The time, the distance it moves before it decays is 0, because we are talking about the proper time. Right? So proper time, proper lifetime means, what do we mean by proper lifetime? Proper lifetime means time measured in a clock attached on the particle, right? Or let me just, sorry. What do we mean by the proper lifetime? Okay, I'll just write it down here. I'll just clarify the information we have from the question. Okay, what do we mean by proper lifetime? Proper lifetime means it's the life, the time or lifetime from a frame in which the particle is at rest. Am I right? In which the particle is at rest. So we are looking at the particle from a frame in which the particle is at rest. All right. So you see that in that frame, the particle just decays. So in that frame, the particle is at rest and it doesn't move. So delta x is 0 in that frame. Am I right? Or dx is 0 in that frame. So we have got here, we just use this equation, c square multiplied by dt, 5 into 10 raised to minus 9, okay, square is equal to, right, c square dt prime square, that's given, right? Am I right? Minus dx prime square. This is clear. So you're looking at the particle from 2 frames. From the rest frame of the particle just sits there and decays. Okay, and we can, so this is actually minus 0. It just sits there and decays. So you're actually calculating, we are actually looking at 2 events. Okay, just explain it more. Just write it here. Okay. Oh, sorry. The question is clear, so I'll just. So the thing is that there are 2 events. Events means you can just draw a time axis and a space axis. Okay, space axis. So I'll just write it as x, t, and x. Now this is the frame of the particle. All right, there are two events. The particle is created here, okay, and it decays. And decays after a time. Okay, so in this frame, the particle does not move and it decays after a time. Okay, and this separation is delta t. Okay, see, there's only movement in the time direction. You see, the particle in the space time, it moves only in the time direction because you are looking at the frame in which this particle is at rest. Okay, now from other frame, you see that the time interval between the same two events is different, 10 into 10 raised to minus 9 seconds. Okay, but now so from other frame, let's write the other frame here. This is from the particle frame, all right, particle rest frame, particle rest frame. Okay, and the same two events, all right, according to the same two events from another frame, let's say t prime x prime frame. Okay, from another frame happens like this. There is this event, the particle starts here, it travels a distance dx. Okay, this distance is dx. Okay, it travels a distance dx and the time taken is, and then it decays in a time dt prime. This is clear. This is the situation. We have got two frames. We have got the rest frame of the particle in which dx equal to 0. Okay, here dx prime. Okay, the particle travels a distance. There's some other frame in which the particle travels a distance dx prime before it decays. Is that clear? And this time is given. This time is given. Right? So we can construct this quantity in both frames. We can construct this quantity in both frames. We are talking about two events, all right? So we can construct this combination in both frames. Okay? In the rest frame of the particle, we have got c square dt square minus 0 because the spatial separation between these two events is 0. Dx is 0, right? Here we have got the here we have got the time separation is 10 into 10 raised to minus 9, and there's also dx prime. Right now, you just equate this and you can solve for dx prime. Is this clear? Fine?
Yes.
All right. So this is the information that you need to use. You can use many problems using this invariant quantity. Okay? All right. So now it's a question of solving this. Dx prime square is equal to, okay, you see that c square into 10 raised to minus 9, so c square, 5 into 10 raised to minus 9, sorry, dx prime, just solve for dx prime, okay, that's equal to c square, 10 into 10 raised to minus 9 square, minus c square, 5 into 10 raised to minus 9 square, okay, so that's, we can pull c square outside, right? So that's 100. Minus 25. Am I right? Multiplied by 10 raised to minus 18. Okay, the square I have pulled. The c square 10 raised to minus 9 square is 10 raised to minus 18. So I just pulled it out. So this is equal to 75. Okay, c square into 10 raised to minus 18. Maybe now you can just substitute c square. So 75 into c square is 9 into 10 raised to minus 16. Am I right?
Yes.
So that's equal to 75 into 9 into 10 raised to minus 2.
Plus 16, sorry. 9 into plus 16,
Yes,
10 raised to.
correct, plus 16. Okay, 3. What's the point? Okay, plus 16. Okay, so that's correct. So we can just multiply. This is dx prime square. Okay, so 675. So 6.75. Dx prime square is something like 6.75. Okay, or dx prime, the distance traveled by the particle, is square root of 6.75. Okay, and you look at the options. All right, when you look at the options, you see that it's the square root is actually given. The square root is actually given. So you see that there's an option 2.6 meter. Okay, approximately 2.6 meter. So you see that if you square 2.6, okay, you can just square it and see it is approximately equal to 6.7, 6.76. I think. If you square 2.6, it's 6.76. So you can say this approximately equal to 2.6 meter. Okay, so if this is given in the options, you just square all the options and check whether it matches with your dx prime square that you found. Okay, or you can just calculate the square root. It's approximately equal to 2.6 meter. All right. So you can solve many problems using this invariance of this particular interval. Okay, this is a Lorentz invariant quantity. All right. Okay, so I think we'll wind up for today. Do you have any doubts? Is this fine? Are you able to follow?
ലോറൻസ് ഇൻവേരിയന്റ് ട്രാൻസ്ഫോർമേഷൻ നമ്മൾ എവിടാ സാറേ അങ്ങനെ ഉപയോഗിക്കേണ്ടതെന്ന് അങ്ങനെ മനസ്സിലാവുന്നേ? വെലോസിറ്റി തന്നിട്ടില്ലെങ്കിലാണോ?
വെലോസിറ്റി തന്നിട്ടുണ്ടെങ്കിലും ചിലപ്പോൾ ഇത് ഉപയോഗിക്കാൻ പറ്റും. It depends. Okay, you have to see. We have to remember that there is such a quantity which is Lorentz invariant. We always have to remember that this quantity c square dt square ds square equal to c square dt square minus dx square. This quantity is Lorentz invariant. You have to remember this. So this also is equal to. So if you can also find the velocity from this, but you don't have to. Okay. So if this is given, if the space, so when do we use this? So that if the space separation is given, space separation and time separation. Okay. If you have the space separation, which is called dx, this is dx, and the time separation is dt or delta t. If these things are given and there's no velocity given, okay, and this time separation in some other frame is also given, and let's say dt prime or dx prime is given, then you can just use this equation, right, if the velocity is not given. Right? Even if the velocity is given, you may be able to solve many problems using this. So you just remember that this quantity is Lorentz invariant and see if you can use it when you solve the problem. Right? You just have to be familiar with this. It's a very important quantity. You have to be familiar with this, and you should be able to use it whenever necessary. So if the space separation and time separation is given in one frame, and you need to find the time separation or space separation in some other frame, okay, space separation means distance, time separation means the time that elapsed between two events. Okay, so if these are the question is given in terms of this dt and dx, okay, and suppose they give dt prime or dx prime in some other frame, okay, then you can just construct this invariant and find either dx prime or dt prime. Okay, this can be done. Or they may ask you to find the proper time. What's the proper time interval? So in some other question they may ask the distance between two, the time separation between two events is given, dx is also given. Okay, that the distance is also given. There are two events E1 and E2 which are separated by a time dt and separated by a distance dx. Okay, they may ask what's the proper time interval. What is the proper time interval? Okay, and then you will have to use the same thing. You just construct c square dt square minus dx square, and you know that this is related to the proper time. This is ds square. And we have already shown that ds square by c square is the proper time. Right? We'll be doing more problems, and then you'll see the situations where we can actually use this relation. Okay. For the time being, it's just one more equation that we can use to solve the problem. All right. One more important piece of information that we can use to solve problems. All right. These relativistically invariant quantities are very, very useful. Right? We'll see later on. Okay. In this problem, this is the only way to solve this. So you just have to, along with the Lorentz transformation equations, you have to be familiar also with this particular equation. Okay, that's the only way to do it.
Okay, sir.
Okay, so if you think that velocity is not given and you are not able to use the Lorentz transformation, then always try to construct this relation and see whether this can be used to solve the problem. Okay.
Okay. Thank you, sir.
Okay. So shall we stop
Thank
for
you, sir.
today?
Okay, thank you, sir.